Greetings again, Tisai, the chiefest of gurus. Now, before we go any further, a couple corrections. When I was saying it, I was like, wait a second. Now, there is a difference between the level of detail required for CSEC and CAPE. And I kind of got caught in the middle when it comes to the Kelvin scale. This is the triple point of water, the upper fixed point, the highest point on the scale is a triple point of water, and that is 0.1 degrees Celsius. The absolute zero temperature is minus 273.15 degrees Celsius. And I put that the triple point of water was 0.15. I was wrong. Now, at your level, the CSEC level, I had to go back and check the syllabus just to confirm more than once. They ignore all these decimals. At the CSEC level, they simply say this is minus 273 degrees Celsius and this is 0 degrees Celsius. So the 0.15 and the 0.16, the 0.5 and the 0.01, they don't consider that. That is why the equation relating temperature in Kelvin to temperature in degrees Celsius, they simply just add 273. Some books you would see 273.15 or 273.16 degrees Celsius. Well, not Celsius. Just, yeah, that. So just had to make that correction clear. At your level, you again repeating, just at the point of sounding annoying, you don't bother with the 0.15, you don't bother with the 0.01. Minus 273 and 0, that's all that is said. Yeah. Two syllabi ran together in my little head, and my little lizard brain couldn't figure it out. Now, moving on. We have to now look at the kinetic theory of matter. Yes, there's a kinetic theory of heat and the kinetic theory of matter, K-I-N-E-T-I-C. Yeah, that sound of water falling. It's 5:40 in the morning and it's raining. So that is the good old sound of a gutter that probably needs to be fixed. But that's a different story for a different day. So the kinetic theory of matter at this level, yes, I have to state that at this level has two main tenets. First of all matter is made up of particles, molecules, molecules. Now these molecules, this is the second part, these molecules are in constant random motion. So these are the two statements within the kinetic theory of matter. Now, I do believe the syllabus requires you to explain the gas laws using the kinetic theory of matter. So let us start with Boyle, B-O-Y-L-E apostrophe S, Boyle's law. Boyle said that for constant temperature, pressure is inversely proportional to volume. When using the kinetic theory of matter to explain the gas laws, we have to remember two things that apply everywhere all the time. The first thing is that temperature affects kinetic energy or velocity of molecules. If you go back to the definition of temperature is defined as a measure of kinetic energy or the kinetic energy of the molecules in a body. That's one. Second thing is pressure. Right? The pressure exerted by a gas comes from collisions with gas molecules. I forgot to see for molecules, forgive me, and the internal walls, internal, of the container. Pressure by a gas. That's the pressure we're talking about here. Now, let us assume, for the sake of argument, that we start off with a container this big. We increase the container size. So, our volume has gone up. This means our pressure should go down. Let's say we have a single molecule. The single molecule takes very little time moving from one wall to the other, colliding and creating pressure in the small container. But when you put that molecule in the bigger container, it takes more time to travel between walls, colliding, creating pressure. So the impression is, from the outside of the container, that pressure has decreased. So if we were to put this in a series of steps, we could say volume has been increased. Interval, actually no, just frequency, one word. Frequency, frequency, of collisions has decreased, and therefore pressure has decreased. And this is how we use the kinetic theory of matter, because you see, the kinetic theory of matter is specifically focused on molecules and molecular behavior. So when using the kinetic theory of matter, we basically have to explain what happens based on molecular behavior. So this is good old Boyle. Moving on to Charles. Lord Charles, I call him Lord Charles, he's not really a lord. Charles said for fixed mass of gas at constant pressure, he said that volume is directly proportional to temperature. So if we increase temperature, we increase volume. So what changes is not, what we change is temperature, not volume. So let us assume we have a container, and this container is held, well, the temperature of the container is lowered. That arrow is way too thick. Yeah, good. The temperature of the container and its contents is lowered. What Charles said is the volume of the container will shrink as well. I know I put going up, but sometimes it's good to actually try going down in temperature instead of going up. Heating is easy to understand. Cooling could be a little more difficult. Now, we have our molecule, and our molecule is zipping about this container really fast, bouncing all over the container, like a kid who's had too much sugar. This molecule now experiences a lowering of temperature. This means if temperature is lowered, Ke is lowered, and velocity is lowered as well. Now the container used in Charles' law is a container that can expand or contract based on the molecular behavior or the behavior of the molecules in the container. If you lower the velocity and the molecule now starts to move like it has aged, it was zipping about, bouncing off the walls, and now it is slowly just chugging along, not bothering anyone, what is going to happen is that the collisions again, the number, the frequency, the rate of collisions is going to decrease. And as such, the container is going to, think of it this way. Think of somebody pushing two things apart, right? If the person is able to exert a great force on the two things they're trying to push apart, they will move them apart. If the person is unable to exert a great force on these two things they're trying to push apart, it's highly unlikely that they will stay apart for very long. So as temperature falls and kinetic energy falls and velocity falls, the volume falls as well. Because the molecules are no longer able to keep the container walls apart. And that is Charles' law. Finally, we have the pressure law. Just so y'all know, I have never done this for another class before. I was supposed to do this since COVID. Now doing it, 3 years late. Horrible, aren't I? So the pressure law states for a fixed mass of gas, a constant volume. Yeah. It says pressure is directly proportional to temperature. And let's raise temperature this time. No. The volume is constant, meaning the size of the container does not change. What changes is temperature. Now, we have our one glorious molecule. Let's assume our molecule is chugging along really slowly. And then we come and apply heat to our gas. And now our molecule has real kinetic energy. It could zoom and zip and fly about the container. The process is always start here. Well, the first thing we changed rather was temperature, so that's where we start. You see, we increase temperature. I should probably use green for contrast. Yeah, we increased temperature. Therefore, KE went up and velocity went up. And therefore, pressure, PRESSURE, goes up as well. Why? Because the number of collisions will increase, or the frequency of collisions will increase. Now, the final thing for this section of the syllabus is heat transfer. Now, let me just state, these videos are just meant to help you revise. That's all. I would never claim they are complete. I would never complain. What did I say? I said complain. I will never claim, that they are complete. I was writing and talking at the same time. I would never claim they're complete. I would never claim that they are thorough. I would never claim that this is the only thing you need to just focus on in order to prepare for the exam. That would be a lie. So, yes, these will help you brush over the broad areas, but you will need to fill in a few extra details on your own. Now, there are three methods of heat transfer: conduction, convection, and radiation. So, conduction. Conduction occurs in solids only. Now, conduction happens because molecules, molecules, in a solid can only vibrate. Molecules in a solid can't move from one place to another. The molecules in a solid can just vibrate. So what happens is these molecules vibrate, and since they're so close, they collide with each other. And basically, by constantly You know Newton's cradle? Have you ever seen Newton's cradle? A series of metallic balls, I think it's five of them, that are suspended vertically. It's like five pendulums side by side. You pull one, you let it go, it swings backwards. After you let it go, it hits the other four, and one at the end pops out. Essentially, that's what happens in a solid, but on a much smaller scale. And the molecules at the ends don't move like they do in Newton's cradle. That does not happen. But it can only vibrate, and that is how he travels in solids, through vibrations. Classic example is leaving a metal pot spoon in a pot while you're cooking. That's conduction. The second method of heat transfer is convection. Convection. And this is in fluids only, FLUIDS. Please remember, a fluid is, fluids rather are liquids and gases. Now, in a fluid, when heated, there is a change in density. The change in density occurs because of expansion. This change in density causes fluid to rise, heated fluid to rise, and in its place falls not so hot fluid. And you have this kind of, I don't want to say cyclic, but it's kind of cyclic process that repeats itself until the fluid is, well, until the fluid is almost at the same temperature, or even. The temperature throughout the fluid is even. Get my words mixed up this morning. Do forgive me. Heated, HEATED, fluid moves. Yes. Transferring heat. And then finally, there is radiation. And radiation is the method of heat transfer through a vacuum. It's how we get heat from the sun. Easiest and best example. Let's say that is us. Let's say that this is the sun. Electromagnetic waves, such as light, travel all the way from the sun to us, bringing heat, light, and other rays through the vacuum of space. And that is radiation. Electromagnetic waves transfer heat through a vacuum. VACUUM, vacuum. All right. This is the end of thermal physics. The next section I will move on to will be waves and optics, which is fun. Not a lot to do in that section. After that, it's electricity and magnetism, and then it is physics of the atom. As always, do like, share, subscribe. Anyways, until next time, stay safe, stay sane, and I'll see you in the next one. Bye bye.